Good morning, good afternoon from wherever you are. My name is Eleanor Warren, and today I'm going to talk a little bit about the relative acoustic attenuation of face masks commonly used during the COVID-19 pandemic. I know for some of my submissions I need to include my experiment conducted date. Due to the nature of my experiment, all of my data was collected on a single day, which was August 6th of last year, and the recording of this presentation was done on February 26th. So I know that my project is classified under physics, and as such, I want to lay a little bit of background for the acoustics side of this. So acoustic attenuation is known as the decibel loss of frequencies that determine the clarity of spoken language. Typically, this indicates clarity in the higher frequencies, as you will see on the speech banana in a couple slides. The closer the numbers are to 0 decibels, the less attenuation there is. Because of the way that I have normalized the control of no mask or my no mask reading to the x-axis of all of my spectrums, you will see that the acoustic attenuation is positive above the axis. So the higher the number, the higher the data point, the more attenuation there is. You will see some that are below the x-axis, and I will explain those when we get to them. Numbers closer to 0 hertz have a lower frequency than numbers closer to 12 kilohertz. This is my sweeps. I went from 100 hertz to 12 kilohertz in my testing. So something closer to 100 hertz has a much lower pitch in frequency than something closer to 12 kilohertz. A frequency plot spectrum logarithmic graph shows the difference of decibel frequencies and what their approximate decibel levels are. I will use this to show my pure tone and audiobook test frequency composition, and then the spectrogram displays the relative signal strength during a particular time in the audio, which I will use with my pure tone test to give you a visual depiction of the readings for each of the masks. Do note that the bottom two were generated in Audacity. This was the software that I used to do most of my data collection. Most of my data analysis was done in Excel. So I want to give a little bit of an introduction with the generalization that face masks pose a problem to deaf and hard of hearing individuals due to lack of access to facial expressions and acoustic attenuation and muffling by masks. In particular, I have noticed this as a hard of hearing student myself. The inspiration from this project came from donating blood with the Red Cross when I realized that I couldn't understand my nurse as well as I should be able to. Fairly recently, published in 2016, a study came out and said that face coverings with an impermeable surface, such as plastic, tend to have more acoustic attenuation than face coverings with a permeable surface, such as fabric. In addition to that, in response to the COVID-19 pandemic, most research surrounds masks primarily accessible by healthcare personnel, such as surgical masks and N95 masks, which are not very ecologically applicable because the CDC recommends that health professionals are the only ones who use these. And since the study was conducted back in August, further research has been published as of October exploring the acoustical effect of different fabric masks. The primary difference between that study and this one is that they tested multiple different weaves and fabric types, while this study tested how designs in particular impacted acoustic attenuation with the same fabric for each mask. If you would like a more in-depth introduction or you would like to see my abstract, please feel free to access my written paper, which has been submitted along with this video for the science fairs. So I would like to give a little bit of an introduction to content of speech and speech frequencies that way. There's something called the speech banana, which includes the majority of the sounds in the English language. You can see it over on the right. I referenced this picture from the University of California at San Francisco. Another thing to keep in mind is the Ling 6 sounds, which are oo, ah, ee, sh, ns. And these have different varying places or varying frequencies as they are common in the English language, from 260 hertz to 5,000 hertz. This just kind of gives you an idea of where the content of English comes from. Something I do want to point out, though, is that if you look on the speech banana over on the far right, you will see the s and th and f sounds. F, S, and TH. Those help determine the clarity of English language. A simple example I can give you is determining singular from plural. If you lose the high frequencies due to attenuation or due to hearing loss, you tend to lose that clarity and understanding of English. With that said, spoken English generally ranges from 150 hertz to 10 kilohertz. In this study, I observed from 100 hertz to 12 kilohertz. This was to make sure that I encompassed all possible frequencies in the English language that may or may not be generated. So my experiment was conducted at the Ohio State University Eye and Ear Institute. I used multiple pieces of equipment, including a foam head with a Sony Bluetooth speaker and a Bcaster microphone in cardioid and mono mode. Both of these have a flat frequency response rate of 20 hertz to 20 kilohertz, again, making it viable to use during the experiment as it went from 100 hertz to 12 kilohertz. I also made my setup about 6 feet apart. This was in order to emulate the recommendations made by the CDC to be in contact with someone 6 feet apart. There are mathematical models in ways to demonstrate how sound changes across distances. So that is a course of research if someone were to want to consider that. So I tested 13 different masks and mask combinations. I did have a control with no mask. As I mentioned before, this reading will be normalized to the x-axis on all of my spectra so that you can see how each mask differs from the control. I tested 1 surgical mask, 2 surgical masks layered, and then 3 surgical masks layered as well, in addition to the N95, KN95, and N95 face shield combination, which is used, in hospital settings. Those particular masks are typically worn for personal safety and will be on their own graph. The furnace filter hospital fabric mask is also considered worn for safety, and it is the only mask of the fabric masks that I tested that has a different fabric composition due to the nature of the mask and the filter. The accordion style fabric mask and the shaped fabric mask are both made, as well as the Clearview fabric mask, are all made with the same fabric and the same number of layers, so the same number of threads per inch and everything, to help demonstrate how the design impacts acoustic attenuation. I also tested the clear mask, which is, a disposable visual access mask, similar to the Clearview fabric mask, as well as a face shield and an engineered Dublin face shield, which I will talk about more later. To begin, I'd like to show you the plot frequency spectrograms. This is so you can see the frequency content of both of my audio samples. The pure tone control went from 100 hertz to 1,000 hertz in increments of 100 hertz, and then from 1,000 hertz to 12 kilohertz in increments of 500 hertz. So this was the pure tone control reading, and then the audiobook control reading over on the right is from a publicly sourced LibriVox recording read by a female reader. It's a 2-minute segment of The Mask of the Red Death by Edgar Allan Poe. I was not without humor in this project. So you can see the frequency response in the audiobook as well, which is on the right. In terms of high interest masks, easily applicable masks to society, we can see, I included on these graphs, these 1 disposable surgical mask, N95, plated fabric mask, Clearview fabric mask, and face shields. Over on the left, we have the pure tone reading, and over on the right, we have the audiobook reading. As most of my results are relative, except for a data table at the end, these results are simply comparable to themselves. So, for example, the face shield and Clearview fabric mask attenuated the most out of this data set, and N95 in the middle, and then pleated fabric mask and 1 disposable surgical mask are about the same. In terms of layered surgical masks, you may be wondering why I chose to include this. This is something that medical professionals are starting to recommend in terms of layering masks to increase personal safety to gain a tighter fit around the face, in particular as published by Gandhi in 2021. Over on the left, we have the pure tone again, And over on the right, we have the audiobook. Something that was very interesting to see, it's particularly visible in the audiobook reading, is that the amount of difference between the control and one surgical mask is bigger than the difference between one surgical mask and two surgical masks, and then two surgical masks to three surgical masks. This demonstrates that as you add each mask, what my study has found is that you gain attenuation, yes, but in lowering increments. This is likely due to tamping down the material to create a smoother surface as opposed to a more pleated surface, which is something that we will see later has a fairly big impact on acoustic attenuation. So masks worn for personal safety as published by Go in 2020 include the N95, KN95, the furnace filter hospital fabric mask, and then the face shield and N95 combination. Unsurprisingly, the face shield and N95 attenuated the most, while the N95 attenuated below that, followed by the furnace filter hospital fabric mask and KN95. Do note that the face shield in N95 is cut off a little bit due to y-axis scaling. However, this was a conscious decision as this is the highest attenuation reading observed out of all of them. So just to keep y-axis scaling consistent, it was cut off a little bit. Something particularly noticeable here, as I mentioned before, is that some of the values recorded dip below the x-axis. This is due to an acoustic resonance effect, where the signal received is stronger than the original signal. So in other words, the signal or the sound coming out of the mask is louder than the sound that was played by the speaker. While this is semi-concerning and should be considered as a possible factor in speech intelligibility, it does not have any impact on acoustic attenuation. In terms of looking at fabric masks, especially as the CDC is recommending homemade masks for environmental concerns, I compared the furnace filter hospital fabric mask, pleated fabric mask, shape style fabric mask, and Clearview fabric mask against each other. With no surprise, the Clearview fabric mask did attenuate the most, again, supporting Sadie as referenced before from 2016, followed by the furnace filtered hospital fabric mask, and then the accordion style fabric mask followed by the shape style fabric mask. Something in particular to note on this slide is that the shape style fabric mask attenuated fairly significantly less than the accordion style fabric mask. This is significant because they both have the same fabric. They both have the same number of layers. The only difference is the design. So in this way, likely what is happening is that the pleats in the accordion style fabric mask kind of act as acoustic foam in the sense that it kind of muffles the sound before it is received by the listener. So this is something to keep in mind across my results. However, as I included in my conclusion, the human ear is only able to detect up to at the lowest 3 decibels of change. There is not a significance of 3. There's not a significance of 3 decibels between the two, and as such, it would not be audibly perceived by the ear in this capacity. But with further research, there can be more clarity on this subject. I mentioned that I would talk about this before. I want to mention it now. I had a couple of students reach out to me from Dublin Kaufman and FRC Team 1014 with some questions about their design, and they wanted me to test their design. The ASL teacher in the Dublin School District reached out to them and said, hey, I've got some deaf students and I really need to give them visual access to lip reading and facial expressions. So they designed this solution. Largely, it is a face shield with fabric on the sides and bottom. This solution was made because the Dublin School District was not going to allow teachers to wear face shields alone, rather a face shield and mask combination. When compared with a model, in particular, of a surgical mask and a face shield, the Dublin mask did have less attenuation overall, and as such, it is being implemented in the school district by request of the teacher and used in multiple classrooms. I want to give a little bit of a spectrogram comparison. This is for the pure tone. in particular, as you can see that the increments increase by 10 hertz, 100 hertz from 100 to 1,000, and then 500 hertz from 1,000 to 12 kilohertz. So when looking at the mask or control, the no mask or control, you can see the baseline reading effectively for each of the tones. And this is the intensity of the signal received. So kind of the loudness, the relative loudness. And we can see here that you lose a lot of the signal strength. So you have a lot of attenuation at higher frequencies, particularly above 3,000 hertz. Something that you can see particularly clearly with the clear mask at 1,500 hertz is that the signal received was stronger than the original signal as denoted by the no mask control. So this is again due to the acoustic resonance effect, and it simply impacts signal strength as opposed to acoustic attenuation. So this is a little bit of a mess, and it is separated on the next slide. But this shows the visual axis masks in relation to each other, including the Clearview fabric mask, clear mask, face shield, and Dublin engineering face shield. Pure tone is again on the left, audiobook is on the right. Something in particular to note is that all of these masks attenuated a lot. And by a lot, I mean a lot. Sometimes up to 30 decibels of attenuation, which is again significant because we can detect up to 3 decibels of change. So spreading these out a little bit, we can see the visual access mask comparison in terms of the Clearview mask and the fabric mask, the Clearview fabric mask and the clear mask, And then over on the right, we have the face shield and Dublin engineered face shield. Please feel free to pause the video if you'd like to look at these graphs a little bit more. I believe that there is a more clear example of this in the data table in the next slide, where you can compare the averages of each mask to each other. So I'm going to kind of try to slide over my video a little bit, but I tested all of the masks and put them all in the data table, and I generated all of the averages between all of them. These are generated across every frequency from 100 hertz to 12 kilohertz on all of them. And as such, these values reflect that. Something in particular, again, to notice is that even for the surgical mask for the audiobook, the average attenuation is higher than that of the shaped fabric mask with the fabric layers. And once again, this kind of gives a little bit of insight into how pleating has an effect on acoustics. Please feel free again to pause the video if you would like to take a further look at this. In column 2, we have the averages for the pure tone test. In column 3, we have averages for the audiobook test. Generally, I have been referencing the audiobook test as there are more increments of measurement, as it is 100 hertz across the spectrum for all of the measurements. And then on the 4th column, we have the maximum attenuation observed, and then the column next to that, over on the far right, is the frequency at which the maximum attenuation did occur. It should be noted that most of the frequencies with the maximum attenuation are very high, and as such would have an impact on clarity of language, as mentioned before with the speech banana. So to give a bit of a conclusion, largely the trade-off seems to be that masks that grant visual access with a non-porous surface, such as face shields and Clearview masks, have the worst attenuation. This is simply due to the surface and material. However, vibration resonance was observed, which again would possibly mask other frequencies. Masks with a tighter fit around the face, also intended for personal safety, attenuated more than masks with a looser fit. And then face masks with pleats generally had more attenuation than face masks without pleats. Like I mentioned before, the biggest change in volume a human can detect is 3 decibels. So the averages and differences between the surgical mask and the shaped fabric mask, for example, would not be easily perceived by the human ear. In terms of choosing masks, there are so many factors to include that's not what this study is observing. My purpose was to elucidate how the acoustic properties of masks have impacted, or how different masks have acoustic properties, as opposed to give a blanket statement on which mask is best. So please do read up on other papers if that's what you are interested in learning. So I would be remiss if I did not have a discussion. Assuming that 1 to 4 kilohertz are the most meaningful frequencies in English, so it is evident that most masks would be less, some masks would be less muffled than others. So likely what this would mean for speech is that the speech would be clearest through something like the shaped fabric mask that on average had less acoustic attenuation than every other mask. And then the speech clarity would be worst through the face shield and N95 combination, which was the mask combination with the most attenuation observed. We did notice that visual access masks have poor sound quality, but the question is, how would this impact communication for deaf individuals? An existing study does show that visual access in the classroom is only offered to students, quote, some of the time. This would include transcripts and closed captioning and visual access masks during instructional situations. So the bigger question here is, how does audiovisual access to communication impact comprehension in deaf and hard of hearing students when masks are utilized in the classroom? This is the bigger application, and largely the application that has an impact on education, particularly in kids. So I have many acknowledgments to make. You know who you are. I've had wonderful mentors. I literally emailed them at the beginning of the summer and said, hey, I've got an idea. And they said, not quite, but I like where you're going. So they helped me develop my project from stage 1, and kept, Dr. Cease Paquette and Dr. Taylor have been amazing for that. I must thank PHONAC for funding my project. I do not declare any conflicting interests. However, they did fund my project. I'd like to thank Ohio State University Eye and Ear Institute for letting me use their space. And then I'd also like to thank Ohio Hands and Voices and Deaf Education Ohio for giving me a chance to speak about my project. Like many projects, I have many references. Please feel free to check them out, particularly in my paper when my analysis is explained a little bit further. So thank you for listening to me talk to my screen for 20 minutes. I hope you've learned something, and yeah, thank you for being here and being willing to listen.